today we're going to tackle this sample problem about finding the theoretical rate law for two elementary steps. And we're not given their rates, so we don't know which one's a slow determining step, which is concerning because knowing that rate, overall rate, is equivalent to the rate determining step, which is the slowest elementary step, we're concerned because we don't know the slowest elementary step. So when that is the case, when we don't know which one it is, we'll just write the rate law for the last reaction, which includes a product. So this also tells us, because we don't know their relative rates, which one's slower, this is going to be a situation that we call the steady state approximation. So that means later on in the steps we're going to take, it's going to be a little bit different than if we knew which step was slower, but we'll get to that in a bit. So the rate, we'll start filling these quantities in. The rate, which is the overall rate, is based on the overall equation, which we did some canceling here, canceled out the intermediates, which are things that are formed in one step and consumed later on. We cancel out the intermediate to give us the overall reaction. So we're going to write a rates law for that reaction, and we don't know the reaction order because it is a multi-step reaction, so we cannot infer the coefficients as the rate orders. So our slowest elementary step. However, for our slowest elementary step, as with any elementary step, we can infer the coefficients as the reaction order for that elementary step. Now, obviously we see that we have an intermediate here, which is not okay. So we have to make an expression that expresses the equivalent of what that intermediate would be. Now, this is very different. How we express this intermediate is different depending on your case. And in the case of a steady state approximation, I'll show you the difference. So in a typical example, if we knew which one was a slow step and which was a quick step, for example, if they said slow and quick, or if they gave you the rate constant for this one and this one, and you found out that this k was smaller than this k, so you knew this one was a slower reaction. So then in that case, use a different color, in that case you would just simply make this statement where equilibrium, in the case of equilibrium, the NO, BR, which is the intermediate, the rate of the intermediate in this first reaction here is equivalent to the rate of the forward reaction. So that would be what you would do if you did know which one was a slow and which one was a quick. And then you would just isolate for this. But because we don't know which one is quick and which one is slow, that means we cannot use this kind of simplicity. We have to complicate it and use a steady state approximation, which tells us that instead of using equilibrium, we're gonna have to not consider equilibrium, but consider the rate of formation of this intermediate to be equivalent to the rate of consumption of this intermediate. So notice how in the first example, if we didn't know which one was slow and which one was fast, we're only using this first equilibrium to get us the expression. However, because we don't know which one is the fast and which one is the slow, we have to use steady state approximation, which means we're going to have to not only use this equation forward and backwards, but also the forward reaction of this. So we're going to use everything basically. So the rate of formation of this intermediate would be the forward reaction. And of course our coefficients are 1. Remember the coefficients or you will lose marks, unfortunately. And the rate of consumption in the reverse reaction, K minus 1, and the reverse reaction would just be NOBR2. That's for the first reaction, since there is an equilibrium, so it's being consumed in this direction. And also the second reaction, where it's being consumed by NOBR2 and NO. And they're all coefficients 1. So then their reaction order of these elementary steps are also 1. So what we have to do next is factor. So these are very complicated steps, and I made another video to walk you through in a more organized fashion. Whoops, whatever that was. Yeah, that was a video. Just kind of reappeared. Okay. So we have to factor out our intermediates because that's what we want to isolate for. So what it's going to look like is NOBR2 coefficients 1. So reaction order is 1 in elementary orders, reaction orders. So now we have to isolate for this. And we're going to also consider this side. So we're isolate. I'm going to bring this to the denominator. So this would be our expression for the intermediate, and we would throw all of this expression for the intermediate in the place of the intermediate in our main problem going on here. So the issue now is that there are 2 k's in the denominator. That's complicated. We don't like that. So we have to impose extreme conditions. And which conditions you impose will depend on the wording of the problem. But if it doesn't say anything, like in this instance, you could probably just do either. So if I'll demonstrate how we could do both of those. So there are 2 restrictions we can impose, and the first one is the idea that the rate of the first reverse reaction is greater than the rate of the second reaction, or the other way around. So if this were the first case, we would just say in the placement of this, we would write instead that K1 would just be in the denominator, since K1 plus K2 is pretty much just K negative 1. And for this instance, we were just saying these 2 plus together, it's basically, this is so negligible, it's basically just this remaining. So this is a pseudo reaction order happening where we're combining 2 Ks together. So you can basically put any one of these depending on the wording of the question based on which rate is faster. You can replace these into the denominator here so that in the end you would get a less complicated equation to work with. So for instance, I'm just going to pick one to finish our problem here. I'm gonna pick where K2 is greater than K1. So I'll just substitute everything in. And always remember your coefficients that become reaction order in elementary states. So for instance, like this here, if you needed to use that, and if it's here, don't forget it. It's the worst mistake you can make. Like after knowing all of this, you make that mistake, it's awful. And then since I'm imposing this extreme condition, so I'll just put this in the denominator. So what you get is a very simplified version, K. Okay, this is K2. K2, K1, K2, so we can just cancel out K2. And then we can actually, let's see. Okay, there's another NO here. That's what I was wondering. See, don't forget to pull everything down. Okay, so because there are two of K2s, one in the denominator, one in the numerator, so we can just cancel out the K2 and just keep a K1. And there's two NOs, so we can just say NO squared. And there's one more NO down here, so let's just cancel it with the top. So overall, this will be our rates. Our rates. But now we have to compare it with the overall rate. And we see that the expression is pretty much in the same form. So we can safely say that in this situation with this circumstance imposed, basically with K equal to K1, this M is equal to N, which are all equal to 1. And since M plus N is the overall reaction order, so this reaction order is 2. And if you use this restriction, this extreme circumstance, you'll find that the overall reaction order is 3. So overall, this equation could be between an overall order of 2 or 3.